Today we're going to do 5.2 graphs of reciprocal trig functions. So you know the three trig functions are, the reciprocal ones are cotan, secant, cosecant, and secant. So by the end of this lesson you'll be able to graph them and you'll be able to determine and describe some of their key properties. Alright, so let's get going. We want to graph cosecant x, and all of you know by now that cosecant x is the reciprocal of sine x. So what we're going to do is we're going to use our understanding of how to graph reciprocal functions that we learned in chapter 3. So we're going to graph the original function, which is sine x, and you all know what sine x looks like, and even now you know that if it has a period of 2 pi, every quarter period it goes from either the middle to the max, and then the max to the middle, and back down to the minimum over these quarter periods. You know all of that. And so what we're going to do is we're going to remember how to graph from a reciprocal, from an original function, a reciprocal. We know, first thing, that if the original crosses the x-axis, that we have asymptotes on our reciprocal. So we're going to go ahead and just bring in those asymptotes. So I will y. Okay, there's 1. There's 2. If we're doing this between 0 and 2 pi, then we don't need to go over past 2 pi, or we don't need to go to this spot over here. It stops at 0. So there we go. We've got the 3 asymptotes. I'm going to label those right now. So this is going to be x equals 0. This one is x equals pi. And this one is x equals 2 pi. Okay. So those are 3 asymptotes on our reciprocal function. Now, the other thing that I think you can remember is that when the graph is at y equals 1, that is a shared point on our reciprocal function. So right here, when y equals 1, we've got a point on our reciprocal function. Similarly, at y equals -1, that's a point of intersection of our original and our reciprocal. So there we go, we've got another point. Okay, and now what does the shape of everything look like in between these asymptotes? This isn't enough to generate the shape of the graph. So we go back to another property that we learned when we were graphing reciprocal functions, and that is that if your graph is increasing on the original function, so as we move along here, we can see that our graph is going up on the original, it's increasing, which means on the reciprocal it will be decreasing over that same interval. So from here, we know that our graph is going to be coming up from here. It was approaching the asymptote here, and now on this part it's decreasing on the original, so this is where it's going to turn and kind of start to increase. It doesn't look too, it is symmetrical and it's kind of bowl shaped. Okay, so that's one part. The same thing's going to happen over here. We can see that as we're moving along our x-axis, our y's are decreasing, so it's going to be the opposite. As we move along our x-axis, our y's are increasing, and vice versa on this side. Okay, so there, I've got my graph. I've got to do a couple things still. I've labeled my asymptotes. I have not labeled a point, so I expect you to label 1 point on each. So this is pi by 2 and 1. This is 3 pi by 2 and -1, and I expect the equation on there too. So this is y equals cosecant x. Okay? All right, that's it. That's all for the first one. Now, I could have generated some extra points here I could have figured out what 3 pi by 4 was, the y value at 3 pi by 4. I could have used my unit circle and my special triangle, my pi by 4 special triangle, and I could have filled in this table of values. But I think that it's really not necessary unless you need to label more points. Okay, So generating a table of values to graph is not a really great idea unless you know the shape of the graph already. Okay, so this was just here to kind of help you, but I think the method that we're using is the tried and true method, really. Okay, let's try the next one. What I would like to see you do is I would like you to pause the video and try this one yourself using the same properties that we learned or that we used in the previous example. So go ahead and pause the video and try it. Okay, so you can see here that I've got cosine function. I want to graph this between 0 and 2 pi again, so I'm only really concerned about from here to here. So I'm not going to put an asymptote here. So I've already drawn in my asymptotes. So now I'm going to go to where y equals 1, which is right here, and where y equals negative 1, and again up here, right? I've got a y equals 1 here at 2 pi, the outer limits of my domain. So using that same kind of property, as we move along here, this way, our y's are decreasing. So as we move along this way, on our reciprocal, our y's are going to increase and approach the asymptote. That's going to happen again over here and over here. Ooh, that's not exactly symmetrical. And over here, this one's increasing, this one should be decreasing till we get to here. And we want to stop because we only wanted to go from 0 to 2 pi. So that is what secant x looks like between 0 and 2 pi. I think I should label my asymptotes. So this is going to be x equals pi by 2, and this is x equals 3 pi by 2. I need to label this point. So this is the point 0, 1, and this is the point pi negative 1. And over here, I'll label this one. This is going to be 2 pi and 1. So label these local maxes and local mins, please, for sec and cosecant. All right, let's keep going. All right, so I have given you the graph of tan here. We just learned that the other day, so I know that one's not rolling off your tongue, but anyway, that's okay. This is the graph, and it's not so pretty. Those are the asymptotes, right? I should really be using these green things here. Okay, so if that's the graph of tan, we want to graph cotan. So we're going to use the same ideas again. We know that if tan is crossing the x-axis, that's an asymptote on cotan. So I'm going to go ahead and drag these asymptotes over everywhere tan crosses the x-axis. There we go. And again, I'm just looking at my domain. I want to go between 0 and 2 pi. So I'm going to go from here. Oh, I don't even have 2 pi on there. So if this is 3 pi, I'm going up by pi by 4s. So if this is 6 pi by 4, one more is 7 pi by 4, and then 8 pi by 4. So I really should extend this graph a little to get 2 pi in. I'll have to change that for next year. Okay, so now that I've gotten my asymptotes in, and maybe I should just, what the heck, I'll just label them while I'm here. So this is x equals 0. This is x equals pi. And now, again, let's think about this. Where there's asymptotes on the original, what do you think those are, what kind of points are those on the reciprocal? So if they were asymptotes on the original, it's because we were dividing by 0. So when we flip that, we actually have 0 in the numerator, which means it's 0 at that point. So this is 0. This is 0. Maybe I'll use red. So red, and red. Oh, well, we don't really, well, you know what, I'm going to go ahead and do it anyway. Okay, so really I should only be graphing between 0 and 2 pi, but because I don't have the 2 pi here, I'll just go into this quadrant. Okay, so this is really from negative pi by 2 to 3 pi by 2. Let's just change our domain here, okay? Okay, so now again, I need to think about more points. I need to generate a shape here. So I know that if I go to where y equals 1, and each square here is worth 1, so if I go to where y equals 1, that's a point on my new graph. And where y equals negative 1, also a point on my new reciprocal function, right? Y equals negative 1 down here. Okay, so what I've got going on here is 3 points. They're not linear, and in fact we can use again what we know. We are increasing over this whole thing really, but we've got an asymptote here. So from here we're increasing here, we're coming from then here, and then we're increasing here, which means we have to be continuing to decrease, right? So over this whole interval we're decreasing, and then when we get over here this is increasing, so we're continuing to decrease all the way along till we get to our asymptote. Okay, so it flattens out and then it kind of does this, and in fact it's just the complete, it's symmetrical to this one, and it's shifted. Okay, so there's one of them. I'm going to do the same thing here. It's just going to come, oh gee whiz. It's going to come down and kind of, it doesn't cross the x-axis like I have here. It's going to come down and then it's going to go this way. And over here, we've only got part of it here. We've got the asymptote, it's coming up from here. And it's oh goodness. There, it's a terrible. It should be doing something like this, right? Okay, at this particular asymptote here. So I'm sorry that's such a mess. It's this pen. So it should look very much symmetrical to the tan graph, but it's also shifted. Okay, so what do we label? We have to label, I would say 3 points. So we should label this one, which is pi by 2, 0. So 3 points on one of the cycles. If we label this one, this is pi by 4 and 1. And over here, this is, oh, no wonder it's kind of funny. It's hard for me to see. I think that's the point there. This is negative 2. So this is 1. So it kind of should have gone like this. And this is, so this point here is, I'm sorry, it's such a mess. There, I'll just redraw that part. So it's the point right here. And we're just going to go something like that. Okay? And that's why this one was kind of awkward as well. Okay, so that's better. So now we've got the point 3 pi by 4 and negative 1. 3 points. I'm going to write somewhere along here y equals cotan x. All right, let's summarize. Now, you can go back to your graphs and think about what the domain of cosecant x is, and what the domain of y equals secant x is. So just go back and have a look and see if you can fill in the domain. Challenge yourself, pause the video, and then I will fill it in for you. So the domain for x, for cosecant x, if you go back to your video, it was sine, which meant that you had zeros at 0. So I'm going to say it's everything, our domain, except that x cannot equal the asymptotes. And we had asymptotes at all the zeros of sine. So the asymptotes, if you go back and look, were at 0, at pi, and at 2 pi, and at 3 pi, etc. Okay, so they're all multiples of pi. So we use that n, remember, to give the multiple. It's multiple of pi. So x cannot equal a multiple of pi where n is an element of the integers. Let's just leave it like that. Okay, so you're going to say it's all possible except the asymptotes, and we've given the equation of the asymptotes here. For sec, which is related to cos, the zeros are at pi by 2 and at 3 pi by 2, etc. So again, we would have x as an element of negative negative infinity to infinity. And x cannot equal, now do you remember how we generated the odd number coefficients? Because the asymptotes for this one are going to be pi by 2, 3 pi by 2, 5 pi by 2, etc. So we've got this odd coefficient in front, the 1, 3, 5, and we generate that using the expression 2n minus 1. We're going to multiply that, that's our odd number generator, by pi, and it's all going to be divided by 2. Okay, where n is an element of I. That's our domain for secant x, and then cotan, that was the one we just did, and it looked like there were asymptotes at the multiples of pi, so we're going to say x is an element of negative infinity to infinity, so everything except n pi, where n is an element of the integers. Okay, for the range, cosecant x, we can start off coming up from the bottom, so from negative infinity, but then we get stopped at our local max, and our local max is going to be at negative 1, and we get to keep that, right? That's part of our graph, so I have a square bracket there. And then we pick it up again at the local minimum, which is at 1, and then to infinity. Okay, so that's the range. For sec, it's the same thing. Okay, let's think about cotan and the range for that. Hopefully you can see that there is no max or min, there's no local maxes or mins. It just goes on forever in both directions, so you're just going to say y is an element of negative infinity to infinity. Okay, what is the period? Well, the period is the length of time it takes for it to repeat, and if you go back and look at cosecant x, you can see that it has the same period as its original function, which is 2 pi. Same for sec, so 2 pi radians. Cotan x repeats over pi, which is the same period as tan. So this one's radian. The equations of the asymptotes over the interval 0 to 2 pi. Okay, well, we know this was multiples of pi right here. So we have that x equals 0, pi, and 2 pi. I think that's sufficient to write it like that. For this one, the asymptotes were the odd coefficients, remember, times pi by 2. So this one would be pi by 2, so x equals pi by 2. And 3 pi by 2. And the last one is the asymptotes were at multiples of pi, so we would have x equals 0 and x equals pi and x equals 2 pi. I believe, we have a word problem to do now. Yeah. Okay, so this is very similar to some of the questions that you'll be asked in your homework. So, when the sun is directly overhead, its rays pass through the atmosphere as shown. So right here, the sun is directly overhead, and we call that, when it hits the Earth's surface, which is here, the Earth's atmosphere, which is here, the distance that the ray takes to penetrate the surface of the Earth is called 1 atmosphere, and that occurs when the sun is directly overhead of the Earth. If you move, the sun moves. Well, does the sun move? In theory, no, but in this example, it looks like it does. So the rays are coming in at a different angle, and we're going to have then an angle x, which is the angle that the sun's rays make with the surface of the earth. That's x. This distance then is much longer, and we're going to call that y, units of atmosphere. Okay, so it says determine an expression for y in terms of angle x. Well, if I need to involve y and x and 1, then they all have to be in the same triangle. So what I'm going to do is I am going to translate this over here. This is 1 unit, and this is a right triangle. And now I have x as part of a right triangle. So I know that if I have to get it in terms of y, then I am going to say, if I stick my pen on x, I know that I could say, I could involve the hypotenuse and the opposite by using sine. Sine x is 1 over y. But that's not going to help me. I'll just show you why. Sine x equals 1 over y. I need something in terms of y, not 1 over y. So let's try it a different way. What if I used cosecant x? So cosecant x, you know, is hypotenuse over opposite, not opposite over hypotenuse. It's the reciprocal. And so if I did that, I end up with y in the numerator over 1. So I end up with y equals cosecant x. Okay? I now have an expression for y in terms of x. Okay. So I'm just going to sort of put an x through this part here. We're not going to use primary trig ratios for this. We're using reciprocal ratios. Okay. So now it wants to graph f of x over the domain from 0 to 2 pi. Pi by 2. And so I would, let's just write our equation. It's y equals cosecant x. And there's a couple of ways you could do this. You could just generate a few points. You know, for instance, that if I wanted to generate, I don't know, let's say I want to go from 0 to pi by 2, I might just choose 3 angles here. So the cosecant of 0, let's think about it. That's 0. Cosecant is the reciprocal of sine. Sine is 0. It's undefined here because 1 over 0 is 0. It is undefined, sorry. Pi by 4, if I go up to pi by 4, there's pi by 4. I know that that's 1 root 2. And cosecant is hypotenuse over opposite, so that's root 2. And for pi by 2, over here at 0, 1, I have 1. And if I take the reciprocal of that, I still have 1. So I could plot these points. This is just one way to do it. So what do I have here? It's hard for me to see. This is pi by 3 and pi by 6. And I chose 1, 2, 3, 4, 5, 6, 8, 9. So over here is halfway between. So this is pi by 4. And now I'm going to draw in my asymptote here at 0. Now you don't have to necessarily draw the asymptote in. But you do, well, you just make sure that you label it, please, at least, and that you're approaching it and not touching that axis when you draw your graph in. So, okay, 0 is undefined. Pi by 4 is root 2. So root 2 is between 1 and 2. So I'll just go ahead and plot something there. And then at pi by 2, it's 1. So we're just going to go ahead. We're approaching the asymptote. We're stopping here, so we're not putting an arrow here because we wanted to go from 0 to pi by 2. Okay, so I've got that. Oh, goodness. I'm just going to... There's a question under there that I need to access, so I'm just going to... I don't know what happened there. Okay. So I'm not sure what the question is, but I think it's asking to what is happening as x approaches 0, what is happening to our y values. And right now, I think maybe what I should do is finish this off, because I didn't label any points, so I'm just going to label at least one point. I'm going to put the equation on there, and might as well label this one while we're at it. And I'm going to label my axes as well, because this is a word problem. So this was the angle the sun's rays make with the Earth in radians, and this was the length of the sun's ray in atmospheres. It's probably like singular. Okay, so can we get less than 1? Could it ever be less than 1? In theory, no, right? Because the sun can't be any closer than overhead, and so this is our minimum, our lowest possible value. So as x approaches 0, what is happening to our y? Our y's are increasing. Okay, so I'll just put, why does this make sense? So put this into context. Explain why the answer to C makes sense, because we know that if you go back to the diagram, that as the angle decreases, the rays must increase. The rays increase as the angle decreases. Okay, and so that's sort of more of a visual here. You can see that if the angle here is getting smaller and smaller, the sun would have to be over here in order for that to happen, which of course would mean that your rays are getting longer and longer. Okay. All right, that's it. That's all. So please do the homework for 5.2. Thanks and good night.